We're going to start today by going over yesterday's homework, which is on page 4 of your book. So these are the answers to the assignment. You're welcome to pause this screen and check over your work. If you have questions, you certainly can raise your hand and ask them. I think maybe the question that I might want to address that I think students will have is with number 12. So I just wanted to show you how you can get the answer to number 12 using your graphing calculator, because really what we need in number 12 is the vertex. If we're going to write the equation in vertex form, you could do this many different ways. So this is the equation here, and you could use a process called completing the square to convert this to vertex form. You could do what I did here, which is calculate the axis of symmetry using x equals negative b over 2a. And then you take that x value, basically the vertex of a parabola is always on the axis of symmetry because it's right in the middle. So whatever the x value is of the axis of symmetry, you just plug that back in to the equation, wherever x is. So y equals 2x squared plus 8x plus 4. You plug that in, and then you get the y value. So that's one way of doing it, but the easiest way is to graph it on your graphing calculator. So I want to show you that so that you know that you could do this. We're going to type in the equation for number 12. Y equals 2x squared plus 8x plus 4. And we're going to look at that graph. And I would like to calculate the vertex. So that is a min value. So I'm going to go second trace, which is calculate, all my calculate options, and I want the minimum. So option 3, and we go to the left of the vertex with our cursor, the right of the vertex with our cursor, and then hit enter. And we see that says negative 1.9999999. So that's actually negative 2. I'm not sure why the calculator says it like this. When you see weird values here, I recommend then going to the table of values to see if this is really negative 2, negative 4. So we'll go to the table, which is right above the graph button, and we look for negative 2, and we see that we have a point negative 2, negative 4. That is your vertex. So we could just use that as our h value and our k value. We already know the a from the original equation. So a equals 2, h equals negative 2, and k equals negative 4. And then you use that information to write the equation. All right, so we're going to move on. In your book, we're going to quickly talk about square root functions because you did a worksheet on this the other day, and you probably have a pretty good idea of how these work. But I want to make sure that you know how they work. So one thing I want you to notice is it says transformations of square root, and then it says functions in all caps. So in order to determine if something is a function, that means for each input, meaning for each number you plug into the equation, which is x, there is exactly one output, which is your y value. That's the definition of a function. So basically, you plug a number in and you get one answer. Well, we know what the graph of y equals x squared looks like. That is the parent quadratic function, so it's a parabola. But what if we try to graph y squared equals x? So I'm not sure if you remember that you already have graphed this. This is actually the inverse. If you notice, the letters x and y are just switched. So if we then solve for y, if we take y squared equals x, and we want to get y alone, we would take the square root of both sides. But when you do that, you have to put a plus minus in front of the square root. That's because a positive number times a positive number could equal a positive number, and a negative number times a negative number is also equal to a positive number. So you're considering all possibilities for what y could equal. If you want more of an explanation of why the plus minus is here, just let me know and I'd be happy to help you with that. But if I were to plot these points, and I'm not going to do it on the calculator, but I just want to talk to you about this a little bit. If I plugged in a negative number, like negative 10, and I would have the positive or negative square root of negative 10. Hopefully you remember that this is an imaginary number. You can't multiply two numbers together to get a negative number. So it's impossible. So this would actually be I radical 10. And you do not have to know how to graph imaginary numbers. So we can't graph them. They're not real numbers. You can learn how to graph them on what's called, we could graph complex numbers on the coordinate plane, but we are not learning that in Math 3. So the smallest perfect square that we can put in here that gives us a nice integer value is 0. Plus or minus the square root of 0 is going to be plus or minus 0, which 0 can't be positive or negative. So the next perfect square we can plug in is 1, and then we would have positive or negative the square root of 1. Well, the square root of 1 is just 1. The next perfect square is 4, and then after that would be 9. So if we plugged in 4, the square root of 4 is 2. We'd have positive or negative 2. And the square root of 9 is 3. So if I were to plug numbers into this equation, these would work. If I plugged in positive or negative 1, if I plug in positive 1 squared, I get 1. If I plug in negative 1 squared, I get 1. So that just shows you that the values actually work. Okay, we're going to plot those points on the graph, so you can go ahead and plot them on that first graph. So we're going to plot 1 positive 1 and 1 negative 1. Then 4 positive 2 and 4 negative 2. And then 9, 3, and 9, negative 3. If we connect those points, it's basically a sideways parabola, which is not a function. It doesn't pass the vertical line test. If I draw a vertical line, it passes through 2 points and it fails the vertical line test. Fails the vertical line test. So it is not a function, but it does exist. This equation exists, and there's a relationship between x and y. It just doesn't meet the definition that we have up here for a function because we get 2 answers. So what do we call something that's not a function? We call this a relation, because there is a relationship. But what we want to study are square root functions. So in order to study a square root function, we're only going to look at the top half of this graph. So we're just going to look at y equals the square root of x. We already have the values. We would just be graphing only the positive numbers. So we would have the point 0, 0, 1, positive 1, 4, positive 2, and 9, 3. And now if we did the vertical line test, it would only pass through 1 point, and this is a function. So that's the function that we're going to be studying. So we are going to write down that the parent function for all square root functions is the graph that we have right here. That's the parent function. It's just y equals the square root of x. And this graph has, instead of calling this a vertex, because a vertex is a turning point, we're just going to call it the starting point. So the starting point is at the origin. The domain is how far left and right. So if we go from left to right on the graph, the first point we're going to come to is this one right here. So that's the furthest left, and then that's at 0, and it goes to the right forever. So the domain is bracket 0 to infinity. We use the bracket because that 0 is included. Now we're looking for range, which tells us how low and how high the function goes. So we look for the lowest point is also at 0. And then how high up does this go? Well, this arrow is pointing to the right, but it's also pointing up. It's not pointing up very steep, but it's pointing up. So the range is also 0 to infinity. So that's the parent function. If we wanted to look at transformations of the parent function, like if we wanted to actually move this function and say it goes, let's say it goes to the right 4 and up 3, then it would look like this. We kind of focus on this point right here and say, okay, this goes 1, 2, 3, 4, and then up 3. And we are now at the point 4, 3. So whatever transformation we do, it's going to shift this starting point. So that's our focal point. So in transformational form, it's just like the vertex form of a quadratic, but we call it transformational form because there is no vertex. So it's a square root of x minus h, and then outside the radical is plus k. So with a quadratic, we had parentheses here and here with squared. This is a square root sign. That's the only difference. It's important that you see that h is still being subtracted from x, and that means that h is still going to be opposite of what we see. So if I see if h equals a negative number, like -3, we're going to see y equals the square root of x minus -3, and that's going to become the square root of x plus 3. So if we start with a negative for h, when we see it in the equation, we're going to see a plus sign. So A still tells us if there's a reflection or not. It tells us if there's a stretch, a compression, and then K shifts the graph up and down. The starting point is going to be whatever H and K are, H comma K. Now the domain, if you look at the transformation I drew up here, the domain would also change. The furthest left is now going to be this 4 right here. This one would be 4 to infinity. So it's whatever H is. And then the range, your lowest point moved up to 3. So that's your K value, and it would go up forever. So the domain is going to be H to infinity, and the range is K to infinity. Now, the only time that would be a little different is if we reflect that over the x-axis. Instead of going to positive infinity, this would go to negative infinity. All right, I would like you to try the 3 problems below, but I do want to point out to you, the first one is pretty easy. Just state the transformations from the parent function. The next easiest problem is number 3, which I spelled right wrong. Write the square root function that has a starting point at 4, -8 is reflected over the x-axis and compressed vertically by a factor of 3/5. Number 2 is the hardest one on the page because it says, write a new function which we will call g of x that transforms f of x. It doesn't say to transform from the parent function. It's talking about transforming this function right here. So start with this and then translate it the way that it tells you to, reflect it over the x-axis, shift it 5 units to the right and down 4 units. So you can do that now. You can pause the video I'm going to put my answers up here. You can push play when you're done. In this one, I just want to show you graphically that if I do this transformation, so we are going to reflect it over the x-axis. So I'm going to start with writing the function, calling it g of x, and I'm going to reflect it. It doesn't say to stretch or compress, so a is still 2. That doesn't change. But I do need to know what h and k are. Right now, they're at the point 3,5. So if I move it from there 5 units to the right, 1, 2, 3, 4, 5, and down 4 units, 1, 2, 3, 4. That means the function that would have looked like this is now actually is reflected. So it would have moved there, but then I'm going to reflect it. So it would look like that. But where did HK end up? So if we were at 3 and I move right 5, that's 8. And I was at 5 and moved down 4. Now we're at the point 8, 1. So H is 8 and K is 1. So that's going to look like this. Some people may have figured it out differently other than by graphing. You could just say if we're going to move right 5, we can do 3 plus 5 to get 8, and down 4, 5 minus 4 gives us 1. And for this one, it doesn't say what to name it, so I'm just going to call it f of x again. And that would be negative 3/5 square root of x minus 4, and then minus 8 outside the radical. Okay. So on this page, I actually just want you to take a look at this. It says write down everything you can about the examples shown below. Now, in a perfect world, you would write down everything you can quietly, not talking to anybody, and then as a class, we would take time to share this up at the board. But since this is a video, I can't do that. So I'm going to ask that you pause the video and just look at this example and look at this example and just write down whatever you think these represent, anything you remember about a problem that looks like this, anything at all. And I'll write down some things that some of my students have said. I'd rather you pause the video though and write some stuff before you push play. -2, we see there's a 1 in both columns. So that means both of these functions contain the point -2, 1. So that has to be the solution. And you see none of the other rows match. That's the only match that there is. So that must be the solution. Some of you may have noticed this is a positive slope. And this is a negative slope. You may have talked about the y-intercepts. You may have said, oh, they both say y equals. Maybe I can solve this algebraically using a method called substitution. If you did, since y equals -x minus 1 and y also equals x plus 3, we can replace y with its equivalent. If y is the same as -x minus 1, then why don't I just put -x minus 1 right here, and then I can solve the equation. So let's show that -x minus 1 equals x plus 3. If I wanted to solve that, I could just put the x's on the same side, and I could put the constants on the other side, and I'd have -2x equals 4. So x is -2. Now that gives me this value right here. How would we get the y value? We would just plug back in. Plug that -2 into either of these original equations. I'd rather work with a positive number, so I'm going to pick the first equation. And there you go. So we can get the same answer by graphing, or we could get it by solving algebraically using substitution. There's also another method that you had learned, which is called elimination. So I'm going to write them both down. Elimination would look like this. We kind of line this up as an addition problem, and we just add each column like this. So y plus y is 2y. The equal sign goes here. X plus -x cancels, and 3 plus -1 is 2. I really should have just written that here. But then divide by 2, so y equals 1. Same thing here. And then to get x, we would just plug it in to either equation. So again, I'll use y equals x plus 3. 1 equals x plus 3. Subtract 3, and we see that -2 equals x. So we get the same answer. Example 2 is already graphed. We're given the equations of the lines, and we're shown that the point of intersection is -4, -7. So one thing I do want to show you is in this class, we would actually write our solution not just as the point -4, -7, but we want to kind of say in a sentence, our solution is -4, -7. And we do that by drawing brackets, which means this is my solution set. So I want you to practice drawing brackets. I know that sounds kind of funny, but the top one is almost like a letter S. And then the bottom is like a reflection of that letter S. So I think of this as 2 S's, which to me means solution set. So anytime we solve something, we're going to use brackets. So if you're not good at drawing those brackets and yours are kind of sloppy, that's fine. That'll work. Squiggly lines, I'll know what you're talking about. And then sometimes people find it easier to draw them kind of like a fancier bracket, like a swirl. And then this one would swirl around that way. So Anyway, practice making some brackets. Try and get them to look pretty neat. And then we'll go to the next page. So this page, I just found some review material, reviewing the steps for the substitution method and showing you where to plug things in. Substituting means you're plugging in one expression for a variable. So here y is the same as negative 2x plus 10, so just get rid of the y and use that instead. The elimination method is the one I just showed you, where you line things up and you add them together and they cancel. The harder type of equations with elimination is if there's nothing that cancels, you have to manipulate the equation and make it cancel. So the good news is you don't actually have to use this method in Math 3. So I may have you skip the problems that kind of amp up the elimination method. Solving graphically, if you recall, you can have two lines that intersect and they have one solution. You could have two lines that coincide, they're one on top of the other, and then you have no solution at all. I mean, you have an infinite number of solutions. Every point is the same. And then you have parallel lines that give you no solution. Then we're going to learn about inequalities. So this is showing us less than or equal to. You shade below and you have a solid line. Greater than or equal to, again, is a solid line, and this is shaded above the line. And then if you put them together as a system, you would have the one below, the one above, and this region right here would be your solution set. So any point in this double shaded region would be a solution. So that's just a quick review of some stuff that you covered in Math 1 and 2. I would like you to work on these problems, but I'm going to let you just, let's see. I think you can maybe try, you can do 1, 2, and 3. 3 is a challenge. You have to write your own equation for number 3, or you can just use trial and error. Solving by substitution, you have to make this say y equals because it doesn't already say it. These are a little bit different. So for this section, you have to make, or actually I'm going to write that you have to isolate one variable. It doesn't have to be the y. You could make this equation say x equals or y equals. And this one, I would make this one say y equals. So subtract the 2x over here, and you'll have y equals negative 2x plus 4. So you have to isolate one variable. So make it say x equals something or y equals something. I would like you to do number 6. In number 7, my hint is that you can subtract instead because you have x and x. If you add them up, that gives you 2x. But if you subtract everything in this row, that will work. You can try numbers 8 and 9 as a challenge. So if you get stuck, don't worry about it. Actually, number 8 is not that bad. So I think you can do number 8. This one is easier, but number 9 might be a challenge. Okay, solve by graphing. So solve each system of inequalities by graphing. You actually would need to graph this on graph paper. You can graph it on your calculator, but I don't know that you know how to shade on your calculator, so you can use your calculator to help you, but I would sketch an actual graph so that you can shade up and down. I just want to remind you that greater than or equal to, less than or equal to. If it's equal to, it's a solid line. So greater than or equal to, less than or equal to would be a solid line. If it's greater than or less than, that would be a dotted line. And I know those look like cute little faces. As far as shading, greater than or less than, if you have greater than or equal to or just greater than, you're going to shade up. And if it's less than and equal to or just less than, you would shade below the line. So that's just a quick review of how that works. And then 13 is just a pretty interesting problem. Give that a try. So when you're finished with these, or actually, you know what? You can do these for homework. Let's make this your homework. And the next, no. That's not what I want. All right, give me a second. Okay, yeah, we'll stop there. So you could work on this in class, and then whatever you don't finish, you can do at home. All right, have a nice day.